Hello, everyone. Thank you for joining my session today. My name is Shinya Kato, and I'm a database engineer at NTT Data Japan Corporation. Today, I will talk about Postgres extensions. The title of my talk is Can We Use Rust to Develop Extensions for Postgres? If you're someone who's passionate about Postgres extensions development or curious about how Rust fits into the picture, this presentation is for you. Let's dive into it. Here we go. Let me introduce myself a little bit. As I said, I'm a database engineer at NTT Data Japan Corporation, which is the largest IT company in Japan. I've been here with our company for about 5 years. I specialize in Postgres, offering technical support, conducting R&D, contributing to the Postgres project, and maintain two key extensions, PG Bulkroad and PG Arma. To begin, can we use Rust to develop extensions for Postgres? Yes, we can. Instead of legacy C language, it's possible to develop Postgres extensions using modern Rust and frameworks. However, getting started with Postgres extension development in Rust can be a little bit challenging due to limited information. This talk aims to provide assistance for developing Postgres extensions using Rust. Furthermore, drawing from my own experience implementing Postgres extensions in Rust, I will share practical insights covering both the pros and cons. While Rust, currently system security is compromised by numerous vulnerabilities caused by memory corruption issues. Google's security team Project Zero reports that about 68% of zero-day vulnerabilities are caused by memory-related problems. These critical memory safety risks are commonly found in C and C++ applications. On the other hand, Rust's strong memory safety features make these issues much less likely to occur. Furthermore, Rust's ownership system guarantees memory safety without sacrificing performance. This is why a partial migration from C and C++ to Rust is underway. For example, we can point to projects like Rust for Linux, which enables implementing Linux kernel modules and device drivers in Rust. Another significant development is Chrome's ongoing migration of its font handling library from C's free type to Rust Scripper to ensure safer font processing. Additionally, in the Postgres ecosystem, Neon is notable for implementing Postgres storage engine in Rust. So how can we implement Postgres extensions in Rust? You can easily develop them using pgrx, which is a framework specially designed for developing Postgres extensions in Rust. Let me explain the key features of pgrx. First, pgrx provides an integrated development environment. Using this environment, you can easily implement Postgres extension features. Second, it safely exposes the Postgres C API to Rust. This allows you to securely call Postgres functions from your Rust implementation. Third, it automatically handles the mapping between Rust types and Postgres types. For example, if a Rust function returns an i32 type, pgrx converts it to the integer type. If it returns an i64 type, it converts it to big int. And if it returns a string type, it converts it to text. There are many popular Postgres extensions written in Rust using pgrx. ParaDB is a modern Elasticsearch alternative built on Postgres. ZomboDB integrates Postgres and Elasticsearch. PostgreSML is a powerful Postgres extension that seamlessly combines data storage and machine learning inference within a database. pgrx is a Rust procedural language handler for Postgres. Various other extensions are also being developed, so please refer to GitHub for more details. Okay, let's move to next part demo. First, let's install pgrx using Cargo. For those unfamiliar with Rust, Cargo is its build system and package manager. Once pgrx is installed, you can set up a development environment for pgrx manage Postgres extensions using the cargo pgrx init command. This might take a little while because it compiles for all Postgres versions currently supported by pgrx. Currently, pgrx supports Postgres versions 13 through 17. Support for version 12 was recently dropped. If you didn't specify a path during cargo pgrx init, you'll find the Postgres source code and data directories located in the .pgrx directory within your home directory. Information about the Postgres installation is stored in config.toml within the .pgrx directory. Okay, let's start developing an extension with pgrx. You can create an extension template using cargo pgrx new extension name. For this demo, we'll create an extension named example. Running this command creates an example directory. You'll see various files have been created. This is actually already a runner Postgres extension. Now, let's run the extension using the cargo pgrx run command. You can specify the Postgres version as a subcommand. We'll use Postgres 17 for this example. Compilation will start. Once it's finished, Postgres will launch and you'll be connected via PSQL. Now, let's use the example extension within Postgres. First, let's enable the example extension in the database using the create extension command. The extension is created successfully. Next, let's check the extension details using \dx. As you can see, the example extension is listed and its description says created by pgrx. We can also use \dx plus to see what's included in the example extension. It seems to contain a function called hello example. Let's try executing the hello example function. Now, let's run select hello example, and it displays hello example. So how is this implemented? Let's take a look. Let's open src/lib.rs. Here we see the definition of the hello example function. It takes no arguments, returns a string, and specifically returns hello example. The pgextern attributes attached to this function is what makes it callable from Postgres. There's also a unit test already implemented named test hello example. Let's run this test. Executing the cargo pgrx test command runs the unit test against all Postgres versions supported by pgrx. And as you can see, the output like test result, okay, one passed. the unit test passes. Alright, that's it for the demo. Based on the explanation so far, I hope you now have a general idea of how to use pgrx. From this point, I like to discuss the pros and cons of pgrx based on my own experience developing extension with it. The first point I'd like to introduce is about setting up the development environment. As you saw in the demo earlier, you can set up the development environment very easily. With the command cargo pgrx init, you can set up development environments for all Postgres versions supported by pgrx from 13 to 17. You can also create an environment for only a specific version for example, using a flag like --pg17. I believe this feature is very user-friendly, especially for beginners in Postgres extension development. However, you can only specify major Postgres versions. Minor versions cannot be specified. While you do not often need to worry about minor versions, the ability to specify them would be convenient. For instance, when you want to check the impact of a bug fixed in a specific minor release. Furthermore, you cannot specify the Postgres master branch, which is currently under development. Developing a Postgres extension isn't a one-time task. It needs to keep pace with Postgres version upgrades. When a new major version of Postgres is released, pgrx will likely add support for it eventually. However, waiting for pgrx to support new major versions after their official release slows down the delivery of updated extensions. If it were possible to develop extensions against the master branch, I believe pgrx would become an even more practical framework for extension development. The second point I'd like to introduce is automatic SQL generation. With pgrx, SQL statements like create function can be generated automatically. But first, let's review how user-defined functions and other components are typically implemented using the traditional C language approach. When implementing a user-defined function called func and providing it as part of an extension using C, you need both a C source file and an SQL file. On the left, I'm showing the C source file, and on the right is the SQL file. After implementing the function logic in C, you then define the SQL function using a create function statement that calls the C function. Furthermore, if your extension provides more complex features like custom types or index support, you also need corresponding SQL definition such as create operator class, or create operator family. As you can see, this means you need to implement and maintain both the C source file and all these SQL definition files. Using pgrx, the SQL file is automatically generated based on the Rust functions, attributes, argument types, and return value types. In the pgx attribute, you specify parameters equivalent to those used in create function, such as immutable, strict, stable, or volatile. Additionally, the Rust function's argument and return value types are mapped directly to the argument type and return type. In the generated create function statement, In this way, automatically generating the SQL reduces the cost of implementing and maintaining SQL files. Similar to functions, pgrx can also generate the necessary create function and create operator statements for operators. Just like before, in the pg operator attribute, you specify parameters for create function such as stable or strict. In the op name attribute, you specify the desired operator name. In the restrict and join attributes, you specify operator-specific parameters. Automatic SQL generation is also available for operator classes similar to functions and operators. However, this capability is currently restricted to B-tree and hash indexes only. Support for other index types like string, gist, and spgist is currently lacking, which is an important limitation to consider. For instance, an extension I developed required gene indexes, so this auto-generation feature wasn't applicable, and I needed to write the necessary SQL definitions directly. The third point I'd like to introduce is memory management. Memory management in the C language requires explicit memory allocation and deallocation using malloc and free. Postgres implementation uses a region-based system for memory management, utilizing memory contexts. This involves creating these memory contexts and allocating memory associated with a specific context. To free memory, you simply delete the memory context, which releases all memory associated with it at once. In this way, Postgres provides an implementation for efficient and relatively easy memory management. However, even with this system, developers still need to be careful about issues like memory leaks, double frees, and dangling pointers. Next, I will very briefly explain Rust memory management. Rust manages memory using a concept called the ownership system, which has three main rules. Each value in Rust has an owner. There can only be one owner at a time. When the owner goes out of scope, the value will be dropped. As shown in this diagram, when S1 is declared, S1 becomes the owner of the hello. Similarly, S2 becomes the owner of world. Next, S2 goes out of scope and then is dropped, freeing its memory. Likewise, S1 goes out of scope and it's dropped, freeing its memory. pgrx memory management system is designed to bridge the gap between Postgres memory context and Rust ownership. Specifically, the allocation of pointers received from the C API is handled by Postgres. Conversely, objects created in Rust are deallocated by Rust itself based on its ownership rule. To help safely manage pointers allocated by C from within Rust, pgrx provides the pgbox type. It's already difficult to understand C and Postgres memory management and Rust memory management individually. Then you also need to learn pgrx memory management. This makes it much harder. Let me give some difficult examples. One is handling memory created in C from your Rust code. Another is passing Rust memory to C and telling Rust not to free it. which goes against Rust's ownership system. The fourth point I'd like to introduce is toolchain. When developing with pgrx, you directly benefit from the rich Rust ecosystem, particularly its excellent toolchain. This familiarity offers great convenience. For instance, you have Carl Clippy for linting to help write more robust and idiomatic Rust. Code style consistency is easily maintained using Cargo FMT for automatic formatting. And crucially for extensions, Cargo pgrx test provides a streamlined way to handle integration testing directly against Postgres. This ability to use standard Rust tooling really makes the development workflow much smoother. Now, let's look at the point marked here as a challenge, which relates to toolchain integration. While the Rust side is well supported, there's currently weaker integration with some traditional Postgres tools. Specifically, as noted here, there isn't direct integration with pgregress, the standard framework for running SQL-level regression tests in the Postgres ecosystem. While pgrx provides its own testing mechanism, it doesn't replace the pgregress workflow. This is a recognized limitation as shown by the GitHub issues listed on the slide. For now, this means that setting up pgregress style tests might require separate configuration. The fifth point I'd like to introduce is documentation. While learning pgrx involves navigating different memory models, as we discussed, there are several excellent resources available to help you. Let me highlight the key ones shown on the slide. First, for the specific details of the pgrx creates functions, types, and macros, your primary reference is docs.rs, which is the API documentation. Next, the pgrx book serves as the official guide and documentation. This is the best place to understand core concepts, learn how to set up your environment, and follow tutorials. Finally, if you want to see practical examples and common patterns, the pgrx examples is invaluable. It contains various code examples that you can learn from the adapt. I highly recommend utilizing these resources as you explore pgrx development. While resources are growing, it's true that there is currently less information available for pgrx development compared to the vast resources accumulated over many years for traditional C extensions. So, because there isn't enough documentation or examples yet, development can still be quite hard sometimes. This is especially true for complex problems or unusual situations. I hope this presentation was helpful for you. Finally, let's discuss the future of Postgres and Rust. There have been multiple proposals in the past suggesting the use of Rust for implementing Postgres core. However, due to various reasons, the adoption of Rust for the core has been deferred. So the chance of this happening is quite low. For example, there's the huge existing C code base, Postgres Unique Memory Management System, and its specific error handling mechanisms, like pgtry. Additionally, Postgres needs to support a wide range of platforms, which presents portability challenges. But as mentioned in this talk, Rust-based Postgres extensions are expected to grow substantially in the future. Okay, let's quickly summarize the main points of this presentation. First, I explained how you can implement Postgres extensions using Rust with the help of pgrx. We also took some time to discuss the pros and cons of using the pgrx framework. pgrx offers a powerful way to build extensions. So let's try it out. Thank you.